This is CS 402 on Wednesday, June 25th, 2014.
Started. Kernel 1, you have a little over a week to do. It's due on Thursday, July 3rd. And, you know, today's weather is not that great. Stay in the lab, work on the kernel assignments. And again, a reminder, if you have code from previous semester, don't copy from it. Best to get rid of it. And again, a reminder that the grading guideline is the only way we will grade, okay? So that applies to warm-up, also applies to the kernel. So make sure you're familiar with it. I mean, if you have a team of a few students, you know, have somebody really read it thoroughly to make sure that, you know, everything is tested according to the grading guidelines, okay? So somebody should be in charge of testing, you know, testing the code, okay? So that nothing gets slipped through. Make sure you tried everything there, and remember we must use the same grading procedure for everyone. And then, you know, if you make a submission, make sure you verify your kernel submission, follow the procedure, okay? Because if you miss the file or messed up, there's really nothing we can do, okay? And it affects the entire team. You can't say, oh, it's that person's fault, you know, give me some partial credit. It doesn't work that way, okay? So your team needs to check each other, make sure everything is done correctly. All right. I got so there's one more person who doesn't have a team. I got a permission from him yesterday to release this information. So John Kotson does not belong to a team. I guess last lecture I announced another student who doesn't have a team. She got snatched up really fast. So again, it's the same deal. If you would like to include him in your team, even if you already have 4 students, I would allow it. So I know it's, you know, it's almost 1 week into the assignment, but you can still, you know, include him in your team. Okay, and this is the only way you can have more than 4 students in your team. All right. Okay. So people have been starting to post stuff in the class Google group. It's great. You can see that, you know, you're getting responses, and you know, clearly some students already know, you know, what's going on. How do these functions mean? And also some people starting to, you know, relate in the kernel assignment with the lectures. And, you know, whatever I said in the lectures, they're all relevant. And you have to read the header files, and you have to read the comment block. You have to read all these code, okay? It's to save your time, right? So I also want to stress that we have test functions. If you read the grading guideline, you will see that there are these tests. One is called Faber test. I guess that one was written by Ted Faber, who I guess used to teach, you know, this class. And Sanghan test is one of my TAs in the regular semester. So you know, so again, you're not supposed to change any other code in the kernel other than, you know, those files you're supposed to modify, right? You're only supposed to submit, you know, what's in the proc submit, you know, inside the make file. Okay, so these files, please don't change them at all. Okay, don't say I'm going to change it to make my code work, and then I'm going to change it back to somehow fix my kernel. That's really not the good way to go. Okay, because you're not allowed to change a single line of these code. Okay, so make sure, you know, so look at these code to see how a process is created and how the thread is created, you know, etc. Okay. And remember, we're doing a single thread per process, all right, even in the kernel. Okay, so read the code. I mean, the Faber test is actually a fairly extensive test, and it tests from, you know, simple stuff to something that's a little more complicated. So it's really a good test to go through. Okay, make sure you understand every line of code there. Okay, what is it trying to do? And if you don't know what it's trying to do, send a message to the class Google group, have a discussion there. All right, so that's sort of a good way to go. If you ask me, what is this function supposed to do? I'm not going to tell you what it's supposed to do. I'm going to say, hey, read the code. Okay, all right. So, I sent an email Monday, says that, the Monday lecture should cover everything for the procs assignment. But towards the end of our kernel assignment number 1, you're supposed to turn on drivers, right? So you're supposed to, interact with the keyboard. So therefore, it's very important to see how interrupts are handled. Okay, so today we're going to start talking about how interrupts are handled. And in the first, 15, 20 minutes, they're going to be code that you can pretty much directly use in your kernel assignment. Okay, so let's try to, understand what's going on here. All right, so section 5.2 cover interrupt handling and cover, some of the topics over here. So we're going to start with talking about the basic interrupt handling. And then we're going to sort of look at, some of the application of interrupt handling, which are very important. One is called defer work, and the other one is called direct processing. The direct processing is another name for, unit signals, right? So you already know how to use Unix signal. Now we're going to see, how it's implemented inside the kernel, okay? And then we also, I guess we're going to also see a special application of defer work, and that will show you how to preempt a thread. All right. Okay, so first, the interrupt handling. We're focusing on dealing with the synchronization and concurrency issues, right? So remember last time I drew this picture, 1, 2, 3, 4. When you try to implement a thread, you got to worry about, synchronizing with other activities on your processors, right? Well, we talk about if you have a uniprocessor, only a single processor, you have to worry about another thread, okay? But if you have a non-preemptive kernel, then you don't really have to worry about it. Okay, if you have multiple processor, then you have to worry about the other thread running on the other processor. They might access the same data structure. Okay, so last time we saw some code. Some of the, the code actually ends up not to be a good solution. And, in the end, we saw the few text code that actually works. Okay, so today we're going to, so look at the other cases where there's interrupt. Okay, so first we're going to divide things into two different situations. One is to look at a case where you have a non-preemptive kernel. Okay, so non-preemptive kernel is what Unix has. Okay, so in this case, you never preempt a thread running in the kernel. Okay, so it's non-preemptive and it's the kernel. User, it's something else, but inside the kernel, it's non-preemptive. Okay, so so in this case, if you want to run another thread, well, one thread has to willingly give up the processor. Okay, and last time we saw code that you can, call thread switch to switch to another thread. Okay, so by the way, in general, if you want to run a thread, how do you run a thread? If you only have a single processor, right? How do you say, well, here's a thread, run it. So what does that mean to run a thread? Okay, the only mechanism that we have seen so far to run a thread is to switch to it, right? There's nothing to say run a thread, right? Because if you have a single processor, you can only run one thread at a time. So the only way you can run a thread is to switch to it. That's the only mechanism in the kernel. Okay? So in the user, how do you run a user thread? It's like, here's a user thread, run it. What does that mean? Right? The only way to run a user thread, and again, you only have a single processor, so you have to somehow switch to it. But if you're inside the kernel, how do you switch to it? Right? There's only one thing that we know how to switch to, something in the user space. So first of all, you have to set up the stack, right? The only way to run to run a thread is to set up the thread control block, to set up the stack, have everything points to the right place, as if that thread was suspended, and then you switch to it. Okay? So similarly, with the user thread, the only way to switch to it is again, you have to set all these things up, and then you have to execute an interrupt return. Okay, the interrupt return is the only way to switch to a user thread. All right, so that's sort of the basics. There's no other way. There's no other mechanism. So if you want things to run, you have to go with these procedures. All right. Okay. So in this case, non-preemptive kernel. So why do we want the non-preemptive kernel? Okay. Well, it makes the kernel really simple. So over here is the number one reason you want a non-preemptive kernel. because you don't have to implement locking inside the kernel. Okay, if I have a kernel thread that's modifying a linked list inside the kernel, okay, do I have to worry about another thread come and access that linked list in the middle of me accessing the linked list? I don't have to worry about it. All I have to do is to make sure I don't let go. Right? I start modifying the linked list, I just keep doing it until I'm done. Only when I'm done, when I'm willingly give out the processor, then it's possible for another thread to access that linked list. Okay, so with the non-preemptive kernel, it's really simple. I don't, when I access all these shared data structure, I don't have to worry about anything. Okay, that makes the kernel implementation very, very simple. Okay, although sometimes, so why do we need a mutex? Right, kernel 1, you're implementing k mutex. So why do you need it? We are doing procs, right? There's no interrupts. There's only another, thread. So why do you need, mutex? Right? If you want to update a linked list, go ahead and modify the linked list. When you're done with the linked list, it's in a consistent state. Well, then you willingly give out the processor, so another thread can never come and do anything to you. Okay, so as it turns out that we need mutex, sometimes we need to synchronize the kernel thread. Okay, so for kernel 1 in the beginning, when you're only doing procs, you don't really need a mutex. Although it's kind of interesting to go through the exercise. I post a message to the class Google group that you might want to think about, once you got the processor and the thread working in the kernel, implement producer consumer. Okay, have a finite buffer. One thread puts stuff here, the other thread takes stuff out. Make sure that runs, and make sure you want to have some interesting interaction going on. So think about how things are supposed to be done. Read, the Faber test code and see how you can, switch from one thread to another. Okay, so that, that's a mutex exercise, right? But if you really have a non-preemptive kernel, you don't really have to worry about other threads getting in the way. Okay, so when you're starting to talk about, devices and stuff like that, then there might be a need for mutex. Okay, so for example, over here you're gonna have an I/O device. You have a device driver here that you want to interact to. Okay, and in order for you to use that particular device, you want to get on the queue of this I/O device. Okay, so one convenient way of doing this, right? So the problem over here is that you want to get on the I/O queue and you want to give up the processor. Okay, so in order to make sure that when you get on this I/O queue, okay, there might be other thread wants to get on this I/O queue. Okay, so once you get inside, you release the processor. But what if another thread come and start accessing this? Okay, so one way to keep the other thread out for accessing the same I/O, because you are waiting for it, well, is to have a mutex right here. Okay, so over here you actually have a mutex. You have to get the mutex in order to get inside the I/O subsystem. Okay, so this way, if you have multiple threads wanting to get into the I/O subsystem, they will actually go in one at a time. Okay, so if you have a situation like that, maybe you end up, you need to have a mutex inside the kernel. All right, so as soon as you turn on in kernel 1, when you get to the end, when you turn drivers equal to 1, you're going to compile some driver code. Well, the driver code is living over here. Okay, and if you set a breakpoint in mutex lock and mutex unlock, you will see that inside over here, the mutex lock and unlock code is going to get called. Okay, because they are doing something like this. All right, so unfortunately for the, for our kernel assignment, you are not provided with the source code of drivers. Because Brown University, they're using that in other places, so I can't really give you the source code. I compiled the binary code, so I can tell you that, mutex lock and unlock is going to be called. Okay, so therefore, in kernel 1, you still have to implement the mutex lock and unlock correctly. All right, because toward the end, they will be used. All right. Okay, so how do you handle interrupt? Let's go back to interrupt. Okay, so if you have a non-preemptive kernel, okay, now you're not going to interfere by other threads. Right, so the only interference that you can come from is going to be in the interrupt. Okay, but it's really easy. You can deal with that. Right, if you have interrupts that are coming onto your processor, and if you're only a single processor and you're doing a non-preemptive kernel, well, all you have to do is to mask an interrupt. Okay, before you touch some data structure that you are shared with the interrupt handler. Okay, so if inside the interrupt handler you need to access a linked list. Okay, in your normal thread, if you want to access the same linked list, well, mask the interrupt, go access the linked list, and I'll mask the interrupt. Problem solved. Okay, so with a non-preemptive kernel, it's really easy to deal with all these kind of stuff. Okay, and Unix is one of these things. All right, what about if you have a preemptive kernel? Okay, so now the clock interrupt is going to come in, and you're going to switch to other threads. So it turns out the solution is very simple. Okay, once you have a preemptive kernel that's all working, if you want to support, you want to change into a preemptive kernel, all you have to do is anytime you want to access one of these variables, you disable preemption. Okay, when you disable preemption, what do you have now? Well, you have a non-preemptive kernel, and you already know what to do. Okay, so it's a very simple right? So you disable preemption. Now the only thing you have to worry about is the interrupt masking. So you mask the interrupt when you have to. And then what about the other processor? Well, the other processor, unfortunately, you have to worry about it a little bit. So you have to use spin lock to lock the other processor out. All right, so we're going to see some, very simple example. How do you, deal with the preemptive kernel? Okay, so first we're going to go back to the non-preemptive kernel and see what we have to do. Okay, so this is interrupt masking. We talked about that before. Okay, so now we have two pieces of code. This is thread code right here, and this is the interrupt handler. Okay, so we're going to have a contrived example where you increment, the value x, both inside the thread code and also inside the interrupt handler, right? So in this case, the shared variable is going to be x right here. Okay, so if you want to make sure that the interrupt handler don't change x at the same time you want to change x, what you have to do is to mask interrupt. Okay, so you mask interrupt right here, and you unmask interrupt right here, and then you're done. Okay, so the specific example we're going to use, remember interrupt, there are two different ways to implement it. One is use a bit vector for interrupt masking, and the other one is use IPL, interrupt privilege level. Okay, so the code we're going to see is using interrupt privilege level. Okay, so set IPL will set the interrupt privilege level to this level, which means that starting from that level, anything lower, less than or equal to this privilege level, they're all blocked. Okay, so in this case, this one will be, the interrupt high level. Okay, so this is the interrupt service routine for this level. Okay, so if you want to block out this particular activity, what you do is you set the interrupt privilege level to this level and block off that and anything lower. Okay, so therefore at this point, as soon as you call this, then this interrupt handler cannot be invoked. Okay, so you know that nobody's going to access, this x in the interrupt context. Okay, so then it's safely to go x equal to x plus 1, and then you need to restore to the previous level. So if you don't want, so one way to do this is to remember what the previous level was before you're here. Okay, so therefore you can remember what the previous level is. So when you call set IPL, you can set the interrupt privilege level to this one. It will also return to you the old privilege level. Okay, so it's almost like, cast, right? When you call cast, it returns the old value to you. Okay, so this is sort of a typical, some of these operating system function works. All right, so when this one calls, it returns the old IPL. I'm going to store it in a local variable right here. Okay, so when I finish accessing X, I will restore the interrupt privilege level to the old IPL. Okay, so let's say that this guy is level 7, right? Okay, if currently interrupt privilege level is at 3, okay, which means that you're probably executing interrupt service routine at level 3. Okay, so the old IPL is going to be equal to 3. You change the interrupt privilege level to equal to 7. Therefore, block out this guy. You change your X, and then you set it back to 3. Okay, if the current interrupt privilege level is equal to 0 for some reason, okay, then you set it back to 0. Okay, so this old IPL plays an important role. It remembers the current context, what the interrupt privilege level is, okay, and then restore it. Okay, so the other way to sort of think about it, this guy actually remember one of the processor state, right? So remember the interrupt enable stuff inside the processor. So in a way, this is trying to remember, currently inside the processor, what privilege level it's set at. So they remember the context right here, and then they restore the context. Okay, so this example only a tiny bit of context information, right, which is the interrupt privilege level. All right. Okay, so this is a really silly example. I mean, who write codes like this? Okay, so let's look at a more realistic example, and this one is going to be trouble. Okay, so we're going to look at yet another very tricky piece of code. Okay, so this is the situation where you have the application called the write system call. It goes into the kernel. Now you're executing the kernel. The kernel says, oh, I have to use a disk write. So it's going to invoke the device driver's disk write to write to the disk. Okay, inside the device driver, it looks like this. Okay, so it writes to the disk. It will start the I/O operation, right? Doesn't matter if it's read or write. It will start the I/O on the disk. Okay, and then so the kernel thread that's running, the code right here inside the file system. That's the thread that's going to call this function. Okay, so it's going to write to the disk and it's going to wait for it, right? Okay, so therefore, what it will have to do is it will have to give up the processor while the disk is doing its thing. So in this case, you will enqueue yourself onto the disk queue. Okay, so therefore the code is, I start the I/O, I'd enqueue myself onto the disk queue, right? Enqueue current thread, which is whoever that's calling this function, enqueue that to the disk wait queue. Okay, so the disk, right? The disk over here, there is a queue in front of it. Every disk has a separate queue. So this one put the current thread and then enqueue on that, into that queue. Okay, and then it has nothing to do, right? Okay, so remember when you call thread switch, you put yourself onto a queue and then you say, I'm giving up the processor, right? Okay, so you call thread switch to give up the processor. Eventually, when thread switch return for this thread, right, which means that the I/O has been completed, that's how you can return. Okay, but for now, you're blocked for several milliseconds. Okay, so over here you disappear, right? So you start to run another thread. All right, so what happened in the disk interrupt, right? So remember in the interrupt handler, what are the two things that are done in the interrupt handler? Number one is to start another I/O operation, right? And number two is to unblock a thread. Okay, so over here in the disk interrupt handler, I will handle the disk interrupt, okay, which means that, I'm going to do some I/O operation, memory map I/O operation, and then start the disk off to do another thing. Okay, so basically take the next job of the I/O queue and then start another operation on the disk. Okay, and then I'm gonna, look at, I'm gonna look at the next one and start an operation. But what about the guy that is sitting right at the head of the queue? That guy has just finished his work, right? Because I'm performing some operation for the job that are sitting at the head of the queue, or for the thread that are sitting at the head of the queue. Okay, so I have to unblock that thread. How do I unblock that thread? I move it to the run queue, right? Okay, so therefore the code over here says I'm going to dequeue the first thread from the disk queue, right? This is the disk queue. Come over here, get the first one, dequeue it. Okay, if thread is not equal to 0, it's kind of silly, right? So this one says if the queue is empty, then I have nothing to do. But if the queue has something on it, then I just finished the job for that thread. If the thread is not equal to empty, I enqueue that thread onto the run queue, right? Basically take this job and move it into the run queue somewhere. All right, so that's what the interrupt handler does, okay? Unblock a job from the, the disk queue and then start another I/O operation. Okay, so this guy will go into the run queue. Eventually, when it makes to the front of the run queue, then what's going to happen? It's going to return from thread switch, right? Okay, so again, this is, how threads switch from one another, right? When you go in there, you go about the processor, you go onto this queue, you made it all the way to the head of the queue, the disk starts an operation for you. In the disk interrupt, you get put back into the run queue, and then you make all the way to the head of the run queue, and somebody's going to call thread switch, and then you return from here, and you execute the next instruction. All right, so as far as this code is concerned, it's almost like, you just continue to execute, except you lost some time during thread switch. Okay, so what's wrong with this code? Okay, what's wrong with this code is that, over here when you start the I/O, what if the disk is so fast, it finished right here? Okay, before you had a chance to enqueue yourself onto the, the disk queue, this guy starts running. Okay, so this guy, when it says dequeue from the disk queue, well, you're not there yet. Okay, so maybe the disk queue is empty, right? So it's going to get confused, and then, so basically what happened is that when you call thread switch, at that point, you never return, because this guy is not going to unblock you. Right? Remember, it's the job of the disk interrupt to unblock this thread, to unblock this thread, put it back on the run queue. Okay, so this is a race condition, because, the I/O finish right here, and the other code starts to execute, and, you're never put back on the run queue. Okay, so the race condition caused a deadlock. Okay, so how do you fix this? Okay, well, we said, well, maybe we should mask the interrupt. Okay, so what happened is that we can do, set IP out, right? We'll put this code around it. Okay, so we don't want the disk to finish too fast, so we don't want the disk to interrupt to happen. So we can put set IPL to be the disk IPL to block out the disk interrupt, so that code doesn't get to execute. Okay, and then we restore the IPL right here. Okay, what's wrong with this code? The disk interrupt never happens, right? Because I do this, I call thread switch, the disk interrupt level is still high. Okay, now when the disk interrupt happens, it's going to become pending. It's going to become pending forever. Okay, so that's another deadlock. So if you put it right here, it doesn't work, right? So what about if you set the IPL low to right here? Okay, if you put move this instruction to right here, and again, the race condition can happen. Okay, it's a no-win situation, right? Okay, so this should remind you about the last lecture, right? We tried to do spin lock here and spin unlock here, and we said there's no place to do spin unlock. The only way, the place you can do the spin unlock is inside thread switch. Okay, and then we say, well, this is really no good because then we have to pass a spin lock inside thread switch to do stuff inside. Okay, so that doesn't work. So then over here we have exactly the same situation. Okay, so what do we have to do? Right? So again, the problem is thread switch. Okay, thread switch give out the processor. So if you leave the interrupt level high, you're going to be in trouble. Okay, so we need to handle thread switch and interrupt at the same time. All right, so we have to do the set IPL old inside thread switch. Okay, but we don't know what it is. Okay, is that okay? All right, so here's the solution. Right, this is going to be a really tricky code again. Okay. So you can actually use almost exactly the same code you're going to use in kernel 1, okay, when you try to implement the switch function in the scheduler. Okay, so let's see the new scheduler, right? So let's go through the O code, right? The O code basically says, O thread is equal to current thread equal to DQ from the run queue, swap contacts and stuff like that. Okay, now you're going to wrap it around set IPL high and set IPL low. Okay, except that this particular code over here, okay, I'm going to set it to the highest priority, highest interrupt priority. Okay, even though the previous one could be for the disk, if for this processor the highest priority is 127, I'm going to set IPL to 127, block everything out. All right, because what was the problem we're trying to solve? Well, is that because in the interrupt handler they want to access the run queue. Okay, so the run queue needs to be protected at all time. Right, that is a linked list. If you access it, in the thread context and in the interrupt context simultaneously, well, you're going to get into trouble. Okay, so in order for us to block out the access of run queue, well, we have to block out every interrupt every possible interrupts. Okay, so over here, what we're going to do is as we come in, we're going to set the interrupt to high, and this one is going to return to us the old IPL. Okay, if you go back to the previous case, what is the old IPL? It's the disk interrupt, right? Okay, so over here, right, we say set IPL to the disk IPL. Okay, and over here, this is the IPL that was before the disk interrupt. Could be 0, could be other stuff. Okay, but now we set the IPL to the disk IPL, and then over here, when you call thread switch, and if you call set IPL, again, it's going to return the disk IPL to you, right? Because that's the current interrupt level. Okay, so we go from, so let's say that the old IPL is equal to 0. This is equal to 0. Okay, the old IPL is equal to 0, and we escalate it to disk. Okay, and then when we go into our routine, we set it to the very high level. All right, so we're sort of playing around with these interrupt level by changing them, from one place to another. All right, so let's go back to here. Okay, so over here, so let's say that, the disk is at, 7, right, disk, okay, is equal to 7, okay, and then the original IPL is equal to 0, okay, and now we set it equal to 127. All right, so now we set it to 127, and now we know we block out all the, all the possible interrupts, right? Okay, so the rule that we're going to use is that anytime you want to use the run queue, well, you have to block out all the other interrupts, because now interrupts are coming, right? Okay, so we have to mask them out. So after you block out the interrupt at all the possible level, now you're okay to look at the run queue. So I'm going to say while run queue empty, I want to see if it's empty. Okay, if the run queue is not empty, then I come right here, right? Okay? And I run here, I run the old code, right? O thread is equal to current thread equal to DQ from the run queue. What is the interrupt privilege level right now? It's 127, right? So I can access the run queue, no problem. I DQ a job from the run queue, I switch contacts, okay? And then I just set IPL, old IPL. Okay? Which thread execute this function? I mean, which thread executed this routine? The new thread, right? So it's kind of weird, okay? So this is my thread, right? I have a thread that looks at the interrupt privilege level like this, and there's another thread, okay? Another thread, well, how does the other thread comes here? Well, they also call the same function, right? So the other thread, when it came here, inside its stack, there's an old IPL. Okay, when I swap contacts, what happened when I swap contacts? I change the stack pointer, right? I point to the other thread stack. So and what's on the top of the stack? Thread switch, right? And inside that thread switch, inside the stack frame, it has the local variable and the function argument. Well, there's no function argument, but there's local variables. It has this guy and it has this guy. Okay, so now that thread is going to execute set IPL to the old IPL. So it's going to set old IPL to whatever that thread was doing. Okay, so that thread might be a interrupt level 0, and when it calls thread switch, so let's say I pretend that thread was doing a pthread mutex lock, or k mutex lock, or something like that. Okay, and then it calls thread switch. So when it comes over here, its old IPL is set as 0, right? But for that thread, it gets escalated to 127. Okay, and now you execute this one for the other thread. The other thread is going to return it back to 0. Okay, and when it returned from thread switch, it returned to whatever it was doing before, and what it was doing before was a pthread mutex lock. Okay, so it's going to return with the lock in its hand. Okay, and the interrupt level is going to be at what? Well, it's at 0, right? Because this guy restored the previous level. Okay, and then eventually, so that's for that thread. But what about eventually when another thread is going to do something, and then our disk thread is going to run again, right? So somebody else is going to switch to our thread, right? This guy, we're going to switch right to this one. This guy, right before it goes to sleep, the interrupt privilege level is at 127, right? So remember, when this thread goes to sleep, the last thing it did was swap contacts. It saved the CPU contacts into this guy and load the contacts for another thread and start running another thread. So at that point, this thread goes to sleep. Eventually, when this thread get woken up again, okay, somebody else is going to call swap contacts, and then we're going to switch back to the stack, and then, in the stack, what is the old IPL? Right, if we're going to return to this thread, old IPL is 7. Okay, so this is the one that called disk write. Okay, so this one is going to set old IPLs to 7, and it's going to execute this one and return, and then what it's going to do next? It's going to return to disk write, right? It's going to return from thread switch, and what's the next instruction? Set IPL to the previous level. Okay, so when you execute this one, you are at interrupt level number 7, which is exactly what you left off right before you call thread switch. Okay, so this guy, before you call thread switch, interrupt privilege level is set at 7 because of this one, disk interrupt is 7. When it returned, it was 7. You restore back to whatever the previous level. Perfect, right? All right, so this code, again, is very tricky. You probably have to look at it a few times to make sure you understand it. Okay? And, okay, so I guess I didn't talk about this part. Okay? What if the run queue is empty? Why would the run queue be empty? Right, so this thread starts a disk operation. It comes over here, switch, thread switch, all IPL is equal to 7, right? So this one gets 7, okay, equal to 7, right? Okay? And the run queue is empty. All right, remember that picture, every thread belongs to a queue except the one that's currently running. Okay, so this guy is going to give out the processor, but the run queue is empty. So that means that nobody is on the run queue. Right? Okay, everybody's waiting for something. Okay, so they're either waiting on a mutex queue, waiting in an IO queue, waiting for, whatever other queue. They're all sitting in a queue somewhere. So what can we do right now? If we have a uniprocessor, we're doing a non-preemptive kernel, what can we do? Nothing. We have nothing to do. All right, so what you do is that, right, so the only thing we can do right now, can we wait for mutex to get unlocked? Wait, who's going to unlock the mutex? A thread, right? But no thread is ready to run. Okay, so we don't have to worry about mutex. Nobody's going to unlock a mutex. So when you unlock a mutex, you move a thread onto the run queue, right? So that's not going to happen right now, okay, because everybody's waiting for something, right? So the only thing that can happen right now is an interrupt. Okay, so you might as well halt the processor and save some, save some energy. Okay, so what you can do right now is I want to, I have nothing to do now, right? Run queue is empty, right? While run queue is empty, I'm going to come over here, set IPR equal to 0. All right, I'm going to set the IPR equal to 0 so that I can do what? Right? It is possible that some interrupt has already occurred while I set my interrupt level to 127. Okay, so they all become pending, right? If I set it equal to 0, boom, the interrupt is going to come in. Okay, when the interrupt comes in, what happens? Something shows up in the run queue, right? Okay, remember that code, right? In the interrupt handler, they start another I/O operation. They move something from the I/O queue to the run queue. Okay, you cannot have an I/O operation without somebody in the in the I/O device queue. Okay, so interrupt happens, right? So over here it says set IPR equal to 0, allow the interrupt to happen, and the next one you execute set IPR high. Okay, so over here there's only sort of a nanosecond executed over here or microsecond. Okay, but then you set IPR low, you set IPR high, you let somebody else come in. Okay, you let interrupt handler to happen, put something in the run queue during this this microsecond. Okay, and then you set interrupt level high. Why do you set interrupt level high? So you can use the run queue, right? You cannot access the run queue unless your interrupt previous level is at 127. Okay, set it to 127 again. Check if the queue is empty. If the queue is still empty for whatever reason, then I'm going to come back over here and do this. Okay, so this might be very wasteful. If interrupt didn't happen, okay, then you set IPR to 0, no interrupt pending, set IPR to high. You're going to go over here in a busy wait. Is that okay? It's not great, right? I mean, you're wasting power, right? So what you can do is that, you set interrupt previous level to 0, and you can actually halt the processor. Okay? You have to sort of, so this code is almost working. You can almost use it in your kernel, kernel 1, except there's a little race condition you have to resolve over here. Okay? Because what happens is that when you, you might want to, halt the processor, but you sort of have to halt the right time. Okay? So there's some additional, interrupt things you have to do to get it to be just right. Okay? Because if you halt the processor right before the processor, right when there's a pending interrupt, okay, then the interrupt can happen, and then you halt the processor. Okay, so that interrupt basically disappears. Well, I mean, that interrupt doesn't really disappear, but your processor go to sleep, right? So you have to wait for another interrupt to wake up your processor. Okay, when the CPU is in a sleeping state, there's only one way to wake it up, and that's from a hardware interrupt. Okay, so this is incomplete. There's a little bit touch-up you have to do, but the other part is, is the way it's supposed to be. All right? So eventually, when it got out of this while loop, interrupt priority level is at 127, and then you switch to another thread. Okay? All right, so this is the magic code that you need to finish kernel 1. All right. For preempted kernel, so for the non-preempted kernel, right, you have to worry about preemption, right? So preempted kernel, that means that the interrupt can come in. Okay, so we already saw how you deal with this particular interrupt on the same processor. Okay, what about this interrupt on the other one? Okay, so it turns out all you have to do is to, disable preemption. And how do you block this guy out? Okay, if I'm running on this processor, right, I'm in the ping thread again. Okay, I want to block this guy out. And this guy's running on the other processor, right? Every processor has an interrupt that can come in, right? There's one of the signal called interrupt. Okay, so if you're running on this processor, and if you disable interrupt, you only disable interrupt on your processor. You didn't disable interrupt on the other processor. Okay, if you want to, how do you disable interrupt on the other processor? Well, you can't, right? You have to execute in that processor to execute the disable interrupt instruction to disable interrupt for me, for my processor. Okay, so therefore, if your code running is on this processor, there's no way for you to disable interrupt on the other processor. Okay, but you can block it, right? You can use spin lock. Okay, so if I use spin lock, right, then whatever the data that I need, the shared data I need to access, I will block this guy out. Okay, but spin lock, you have to use it very carefully because you only have to use it for a very short period of time. So you got to make sure that that's what's going on. Okay, so the way to do this, okay, so clearly you cannot use spin lock like this, okay, because the thread doesn't really work well with interrupt. All right, because this will cause a deadlock situation, right? You locked over here, you get an interrupt, then this is not going to work, okay? And it's not going to work because this guy is running inside the same processor, okay? When this guy's on the other processor, then they can execute in parallel, right? But if this is the same processor, then it's not going to work, okay? You really have no control of whether this interrupt service routine is going to execute in one processor or the other processor. Right, because if you have a machine that has a quad-core machine that you have on your laptop or on your cell phone or something like that, all the cores are identical, right? So you can't really say, oh, this one I don't want to run interrupt handler on this one. If it happens on this processor, it happens on this processor. Okay, so using the spin lock, it's not going to work when this interrupt happens on your own processor. Okay, it's going to cause a deadlock, right? So here's the solution. Okay, so what happens is that I'm going to disable preemption. Okay, as I mentioned before, right? And then mask the interrupt on this processor. Okay, so when I do the first one, disable preemption, 1, 2, 3, 4, which one can't happen anymore? Right, I'm the ping thread, I'm executing this code. Okay, 2 can't happen anymore, right? When I say disable preemption, well then this guy won't run, number 2 won't run. Okay, when I mask interrupt, okay, which one can happen anymore? Number 1 can't happen anymore, right? Okay, so the only thing I have to worry about is 3 and 4. So if I do a spin lock right here, I'm going to block out these guys out there. Okay, so this action, spin lock over here, take care of number 3 and 4. Anything happen on the other processor, they have to obtain the spin lock before they can come and do stuff over here. Okay, so this is actually the right sequence. You have to do it in this sequence. Okay, otherwise it's not going to work. Okay, what about interrupt happening on your own processor? Well, so if this code is executed on the other processor, the spin lock is going to prevent it from happening. But on your own processor, well, it's the masking of the interrupt is going to prevent this code from happening. Right? So if you mask the interrupt, and if this code is going to execute on your own processor, you don't have to worry about the spin lock because it never gets in here. Right? Because the interrupt has been masked. All right? So again, this code is, a little not so obvious, but look at it a few times to make sure that you're convinced that this code actually works. Okay, so I guess we're done with with the interrupt handling. Okay, so you should be able to finish your kernel 1. All right, the next thing we're going to talk about related to interrupt is something called defer work. Okay, so remember I mentioned that in interrupt handler you need to do as little as possible. Okay, what if you end up you have to do a lot? Because this interrupt you have a lot of work to do. Okay. So what you can do is that you can have those work to be done at a later time. Okay, so that's what it means by defer work. Okay, there's stuff that you're supposed to do in an interrupt handler. Okay, but you want to minimize the amount of execution time that you spend in the interrupt handler. So all the stuff that you're supposed to do in an interrupt handler, you need to do it at a different time. Okay, you need to defer the processing of those work at a different time. So the question is, when do you do it? Okay, so that we're going to try to answer that question. Okay, one of the example is going to be in networking. Okay, in networking, what happens is that inside the interrupt handler, right, you have a packet coming from the internet, hit your machine, and then go into the network interface controller. Right, so over here, a packet coming from the internet hit your network interface controller. Okay, and that piece of data get DMA'd, right, direct memory access, transfer into main memory, right, DMA into main memory, okay, and then you interrupt the processor, say, hey, there's something, there's a packet that needs to be processed. Okay, so during the interrupt service routine, right, inside the driver, there's an interrupt service routine right here. That one needs to go into memory and try to process that data. Okay, unfortunately, in the in networking, there's actually a lot of work to do. Okay, so we don't want to burden too much of this guy. Okay, so we sort of want to have most of the work deferred, and inside the interrupt handler over here, we'll only do the crucial work. Right? Again, what are the crucial work? You start another I/O operation, and then you unblock a thread. Okay, so in this case, if there's a thread waiting for this particular packet, then you need to unblock that thread. Okay, but also there's one more thing that you can do now, because you have all these work you need to be done. You need to generate this work and defer it to do at a different time. All right, so over here now there are three things in addition to those usual two, is to create the defer work, put it in a queue somewhere so that somebody else can do it later on. Okay, so who is somebody else? Well, pretty much any kernel thread can do it. Okay, because this job needs to be done in the kernel. Okay, so what happens is when a packet arrives onto your machine, the networking subsystem is going to kick into action. Okay, and the networking subsystem in modern days is called TCP/IP. What they need to do is to examine this piece of data coming from the internet, and take it's a packet, right? We're seeing packet in warm-up 2, but those are really not real packets, right? We'll pretend that they're real packet. So these are the packet processing you have to perform. What you need to do is you need to go into this data, look at every byte, and parse this data into header and data, and then pass it up to another layer inside the networking subsystem, and that guy has to parse it and then decide where to go up and where to go up, where to go up. Okay, so this thing actually gets transferred several level, up the protocol stack, and all these work needs to be done inside the kernel. Okay, so these are, there's a lot of work that needs to be done. You don't want to do it at an interrupt handler, but are these important work? If you think about what the kernel has to do, right? The kernel has to handle interrupt, and then they have to handle system calls, right? Okay, and then if the kernel has nothing to do, you run the user threads. Okay, so this is actually pretty important work. It needs to be done before running user threads. Okay, but it's all this other work that are deferred, are they more important than interrupt handling? No, right? Because interrupt handling, when interrupt comes, you want to finish all those stuff as soon as possible. So this work is really not as important as any of the interrupts. Okay, so if you think about the priority, this priority is actually pretty low. It's higher than user threads, okay, but it's lower than all the interrupt handling. Okay, so that sort of tell you, when this thing needs to be done. All right, so the deferred processing code sort of looks like this. Okay, so the idea over here is that if we look at, so let's pretend that we have a thread making a system call, and then, it goes into the operating system, right? So over here, you have a user stack we're not drawing, right? User stack. So inside the kernel stack, this is the kernel stack that's handling the system call, and now interrupt starting to happen. Interrupt 7 happens. Interrupt 7 runs for a while, and then interrupt 15 happens. And interrupt 23 happens. So your kernel stack looks just like this. Okay, so there are many stack frames. Okay, and now interrupt 23 is the networking interrupt. Okay, and this guy needs to do some defer work. Okay, so when do you do that? Okay, do you do that before interrupt 15? Right, because when this guy finishes, it needs to return to complete interrupt 15's handling. Okay, so should you do the defer work before interrupt 15 finishes? No, right, because interrupt 15 is pretty important, right? Okay, so therefore, do you do it right here? No. Do you do it right here? Maybe, right? This might be a good time, right? When interrupt 7 is finished, you're going to return back to service the system call. Okay, so now you're doing things on behalf of the user. Well, that's not as important as networking processing. Okay, so this is the right time, right when you go back to, to the thread context. Okay, that may be the time when that you need to do defer work. Okay, so therefore, what is the kernel code going to look like? If we have a top-level interrupt handler, right, every interrupt comes here, including system call. Okay, what we need to do is that we need to handle the interrupt. So over here, it says we're going to, whatever the interrupt is, we're going to call the device-specific interrupt to handle it. Okay, when this guy returns, what we need to do is that we need to look at the kernel stack and look at the previous stack frame right before it. And we say, is the previous stack frame is in the thread context? Okay, so over here, if we're returning from, right, so over here, interrupt vector returns. Over here, we'll be returning from this guy. we will look at the previous diagram and say this one is an interrupt context, so it's not a thread context. Okay, so therefore this one will return false. If we're returning from interrupt number 15 service routine, then again we're going to return false. And then if we are returning from interrupt 7's service routine, then if we check previous contact equal to thread context, and now we're going to return true. Okay, so this is only true right here when this function returns. Okay, so therefore over here, what we do is that we unmask interrupts. Okay, we allow other interrupt to happen. Okay, so over here, right, when we're servicing an interrupt, okay, the interrupt, we're gonna mess around with the privilege level. Okay, we're gonna block out all the interrupt, 7 interrupt right here, block all the 15, block all the 23. So when you come back over here, you're gonna return back into the thread context, and the thread context interrupt privilege level is pretty low. Okay, like 0 or 1 or something like that. Okay, so over here we're gonna allow interrupt to happen because again, interrupt is more important than the defer work. Okay, we're gonna unmask the interrupt, and then we're gonna go to this work queue for the defer work, and we're gonna say while the work queue is not empty. Okay, we're gonna dequeue the work, a piece of work from the work queue, and we're gonna, invoke that work, via a function pointer and to call it. All right, so this code is pseudocode, right? So it says, go to this work queue. So the work queue is a defer work queue. Okay, dequeue a job, a work from it, and then invoke that piece of work. Okay, so how do you add work onto this particular queue? Okay. So over here, here's an example. In the network interrupt handler, I do those two things first. Okay, start off another I/O operation, and then unblock a thread, and then I enqueue more work onto the work queue. Okay, so all that processing of parsing the header and the body of the message inside memory, those are the defer work, right? So I'm gonna create this more work and queue that to the work queue. Okay, so work queue in this example, right, work queue is just a list of function pointers. Okay, so when I add this function onto the function pointer, well, then it get invoked. Okay, of course, it will take more arguments like, function arguments and stuff like that, right? But this is just pseudocode. Okay, so when you have any defer work, all you have to do is to add them to the work queue, and then this code will execute them at the right time. Okay, and the right time is right before you're going to return to the thread context. Then you're going to add this, another piece of work on top of the stack, okay, by calling this function. All right? Okay, so I guess this is the first time I actually see how Windows does things. Okay, Windows, for deferred processing, it has an interrupt level. Okay, so DPC, the deferred processing, so I guess DPC stands for defer procedure call. Okay, the deferred procedure call actually has an interrupt level, and it's interrupt level 2. Okay, all the hardware interrupt are from level 3 all the way up to, over here is 31. Sometimes it can go up to 127. Okay, thread context is the interrupt level 0. So if you set IPL equal to 0, well, that means that there's no interrupt, right? You're at the thread context. Okay, there's actually one thing between them, and that's called APC. Okay, APC is very similar to Unix signals. Okay, so it's like you're doing something on behalf of the user. So this one has, slightly more higher priority than 0. Okay, and we're going to see APC next. Okay, so right now we're focusing on DPC. Okay, so this is the interrupt level. Okay, so therefore when you queue that piece of work onto the work queue, okay, what you're supposed to do also, you're supposed to create a software interrupt. Okay, so over here, this guy on Windows, this is actually considered a software interrupt. So you can actually generate a software interrupt at the level 2, and that will cause this interrupt handler to get, I guess if at the current time the interrupt level is higher than 2, then interrupt level 2 will become pending, right? And eventually when you're ready to return to either interrupt level 0 or 1, that's when this interrupt is going to get delivered. Okay, so if you go back to that picture again, it will be delivered right at this time. Right, because everything below here are hardware interrupts. Okay, so if you generate a software interrupt, the software interrupt is going to be pending until all these things are popped. Right before you go back to the thread context, and then the interrupt service routine is going to kick in, and then you will execute interrupt level number 2. Okay, in that case, interrupt number 2 is going to execute this code. Okay, so therefore the code is slightly different. Okay, is going to look at this, right? So in the interrupt handler, okay, if you decide to add some work, right, you enqueue the deferred processing work. Okay, you're going to add the more work function onto that queue, and then you will request a DPC interrupt. Okay, so over here, this is how you generate interrupt level number 2. Okay, so that, and if you're running at a higher level interrupt, this interrupt will become pending, and when you go back to 0 or 1, that's when this interrupt is going to get invoked. Okay, so this DPC handler is the handler for interrupt level number 2, and inside this code, all it does is the following. Okay, all it does is to check if this DPC queue is empty or not. If the DPC queue is not empty, it dequeue a piece of work, and then it invoke that piece of work. All right, so you keep doing this until there's no defer work. All right, so this is how defer processing is done. For Linux sort of handle things a little differently. Linux actually has a software interrupt threads. Okay, so all the DPC work are done in a separate thread. Okay, so if there's no DPC work, that thread is suspended. As soon as you have some work, for that thread gets woken up. So how do you wake up by something like that? Well, you can wait on a signal, or something like that, right? You can wait on, I guess, if you're implementing P threads and you're waiting on a condition variable, but if you're, using something like a semaphore, you're waiting on a semaphore. Okay, so this thread, this is the software interrupt thread. Okay, so you go into an infinite loop. Okay, it says you wait for an event to be signaled. When this event is signaled, then, you go to the DPC queue, or in this case, you go to the work queue and keep, running all the work over there. Okay? Inside the interrupt handler, if you have deferred work that needs to be done, what you do is you enqueue that work onto the work queue, and then you signal the event so that this guy can be unblocked. All right? So different approach, they both work. Okay, so one of the example of a delay processing, right? We saw, networking is one example. The other one that you can do is actually thread preemption. Okay, when you try to preempt a thread, right? You have a thread running on the CPU, and you assign it a quota. Okay, and this thread uses up its quota. You want to kick it off, right? So how do you kick a thread off the CPU? Okay, this thread is not giving up the CPU voluntarily, so you have to, remove it. Okay, so what you do is set a timer. When a timer interrupt happens, you get a hardware interrupt, right? So now you're in the kernel, and the kernel can actually decide to switch this thread out. Okay, so when do you switch this thread out? The answer is during deferred processing time, right? Because that's really the best time to do it, right? You want to do this before any of the thing that you have to execute in the thread context, but you want to do this at a lower priority than all the interrupt that you have to do, right? So that's exactly the deferred processing time. Okay, so you can actually implement thread preemption doing this. So in the clock handler, okay, so you say, well, you get a clock interrupt. So, well, why do I get a clock interrupt? Oh, because, for the current running thread, the time slot is over. Okay, so now you have one thread that's running, right? This thread just used up its time slice. So therefore, when you're executing in the kernel thread is going to borrow the stack from, this user process. Right, so you're exactly the right place to switch this thread out. Okay, so this guy, you check whether the time slice for this thread is over. If it's over, in this case, so it's almost like our warm-up number 2, right? In the interrupts in the signal handler, you set a global variable and then you're done. Okay, so over here we set a global variable to say we should reschedule this thread. Okay, so when is this guy actually done? The rescheduling. Right, so over here in the interrupt handler, you do as little as possible. You set a global variable says, hey, when I'm going to return back to the thread context, that's when I need to, do the rescheduling. Okay, so over here, again, you have the top level interrupt handler, the same thing as before, right? Over here, all the same as the code before. Okay, right before you're going to return to the thread context, you check, okay, whether we should reschedule. Okay, if we should reschedule, we call, reschedule. Okay, so remember who is executing this code, right? This is going to be the kernel thread for the user's thread that's using up too much time. Okay, so therefore this guy, when I call reschedule, is going to switch to a different thread. All right? Okay, this also works inside a trap handler. if you are, trapped into the operating system, right, you can execute a trap specific handler, right, and then there's 256 different traps, right, read, write, fork, and stuff like that. When this guy is returning, okay, right before you're going to return to user space, and again, this is the right time to check whether you should reschedule or not. Okay, and who is executing this one? Again, it's the kernel thread for the corresponding user thread that used up too much time. Okay, so in this case, that thread used up too much time in what? Okay, well, it's handling some kind of a trap, right? So therefore, it's using up, too much time while it's, while it's sitting on the CPU. While it's servicing a system call, right? If you make a system call and inside the kernel, you use up too much time. Well, this time it's the kernel that's trying to servicing a system call, right? So the time that you spend in the kernel should be charged to your user process. Okay, so therefore, again, this is the right place because that's the thread that that use up too much time. Okay, so again, you call reschedule to give the CPU to another thread. Don't return to that thread. Return to a different thread. All right, so that's what the reschedule does. All right, return to a different thread. Okay, so this is for user mode. What if you have a kernel preemption? Okay, so now you're running in the kernel thread. Okay, so in kernel, you have a preempted kernel. You set a clock interrupt so that when a kernel thread uses up too much time, okay, you also want to switch to a different thread. All right, so this is a different kind of. So by the way, we at the beginning of today's lecture we said that non-preempted kernel is nice and clean, right? You don't have to do locking in the kernel. So why do these days, if you look at all the real operating systems that are out there, they all have preemptive kernel. Okay, and the reason is because preemption is very important to have good performance. Okay, if you allow a kernel thread to hog the CPU, okay, so what kind of a kernel thread can hog the CPU when you don't expect it to? I mean, if you think about Unix, right? You're implementing the entire kernel. You know when every thread runs, how long it's going to run, right? So where are the things that you don't expect? Right, it's the device drivers. Okay, the device driver, if you're in your operating system, there's going to be 10,000 device drivers. Every one of them is going to run in a kernel thread context. Okay, so therefore those guys, if it goes on forever, if it locks up, if it has an infinite loop inside a device driver, and if you don't have a preempted kernel, you're going to be in big trouble. Okay, so therefore any real operating system, they have to implement a preempted kernel. Okay, and you have to take care of the case where a kernel thread is going to use up too much of the CPU. Okay, so in that case, you want to switch to another thread. So again, when do you switch it? Okay, so interrupt handler over here. Okay, again, the clock interrupt. You check whether this clock interrupt is because of the current thread using up too much time. If it is over here, well, you can just add, to the deferred processing queue, reschedule. Okay, so we already know how this works, right? You add a work to it, and then you create a software interrupt to. So I guess this is Windows code, right? So if you do this, you're gonna call the interrupt on number 2 or something like that. I mean, this interrupt 2 is not Control C in the user space. This is in the kernel. Okay, so interrupt 2 in the Windows is the DPC interrupt. Okay, so this one is going to add this piece of code called reschedule into DPC code, and we're ready to see how that code is going to get invoked. Okay, so therefore, right before you switch back to this thread context, that's when you switch to run a different thread. All right, in this case, it would be a different kernel thread. All right. Okay, so that's the default work. Okay, the next thing we're going to look at is direct processing. So direct processing, APC, this is in Windows. Okay, and this is in Unix and Linux. So one of the main differences between Windows and Unix is that Unix signals is strictly for user processes. Okay, you cannot have a signal handler inside the kernel. Okay, the kernel doesn't really know anything about signals. All it knows about is about upcall. Right, when the user process set up a signal handler, that means that when something happens in the kernel, it needs to make an upcall on behalf of the user process. Okay, so signal is only a user space, thing. In Windows, they have a more general mechanism, Okay, inside the kernel, you can also do direct processing, which means that direct processing meaning that when this event happened, call this function. Right? So certainly in signal handling, I would say when control C happened, call this function. When I receive this signal, call this function. When I do a divide by 0, call this function, right? So it's all direct processing. Okay? So window mechanism is a little more general. You can do it inside the kernel. All right? Okay, so I guess this page talk about the differences. Okay, so if you go back and think about warm-up number 2, right? Here's your user process. Okay, and then in the text segment over here, you have a signal handler. Okay, signal handler right here. Okay, what you do is that you say, well, when Control C is pressed, call this function. Okay, so how does that really done, right? So let's pretend that you only have a single thread, right? You have a single thread running in your user address space, okay? And that one is doing something, some infinite loop or something like that. Control C is pressed, right? We talked about it before. What's going to happen is that we're going to borrow that thread to run this code, okay? And this code is going to be run in the user context, right? Okay, so in the user, there's only one thread, so therefore, it's this thread gets suspended, and this thread is used to run this function. So what does that mean, this thread is used to run this function, right? When you have a thread, right, you have a stack. So this guy has a stack right here inside this thing, okay? It's doing something, and then we're going to borrow this thread to execute this function, okay? Which means that we're going to use the same stack. We're not going to allocate a new stack because that's just too slow, okay? We're going to use the same stack, and we're going to make the stack this, the signal handler. We're going to push onto the stack the signal handler, and we're going to use this thread, meaning I use that thread control block, okay, set up the context so that when we return, we're going to execute this code right here. The stack pointer will point right here. The instruction pointer will point right here. Okay, so it's kind of like a magic trick that the kernel does, but the kernel is all powerful, so it can play any kind of magic trick that it wants. It will set up the user stack and set up the user context so that, when the user thread execute again, it will execute this code and the stack will look like this. Okay, what about when the interrupt service routine, when the signal handler return, where should it return to? Well, I need to return to whatever the user was doing. Right, and what was the user doing before? Well, I don't know. It was doing whatever it was doing, right? So the user was using the stack, was happily using the stack. The stack pointer was pointing over here, and all of a sudden the user pressed Control C, right? Which, of course, the user process has no control when that can happen because the user, there's no synchronization happening, right? So the user pressed Control C, and now, you have to save the current state, right? Again, you have to save the context so that you can restore the context later. Okay, so we got to save the context somewhere into a special place. Okay, so where is this special place is going to be? Well, it has a stack, right? Why don't we store it right here? Okay, so it turns out that this user stack, right, this was whatever it was doing before the stack pointer is pointing right here. So the way we're going to solve this problem is that we're actually going to build a funny stack frame right here, okay, to store the actual entire context of this interrupted thread, okay, and put it in here. Okay, and then we're going to create another stack frame for this, for the signal handler. All right, and we're going to change the instruction pointer to the signal handler. Okay, and then have the stack pointer point right here, as if we are executing this function. Okay, for those of you who have done this in warm-up number 2, if you set a breakpoint inside the handler and you do a where, what do you see? Do you see all the way to main? No, you can't see it, right? Because there's a funny stack frame over here. GDB says, what is that? Okay, GDB doesn't know what's over here. Okay, so therefore, when you are executing in the interrupt handler, if you do a where, all you see is this stack frame. Okay, there's nothing over here. Well, there's actually something over here, but you can't see through this funny stack frame because this is not a regular stack frame. Right? What is this stack frame? Well, it's kind of like a special interrupt kind of, because over here, right, you press the Control C, okay, so your entire processor state for wherever your thread was executing, the entire state of the processor needs to be saved right here. Okay, every register, whatever, they all have to go in here. Okay, so where did that information come from? right? So if you go back to the hardware abstraction layer, right, when you get an interrupt during the time of, transition from the hardware all the way back into the operating system, there's this hardware abstraction layer. It's sort of, you push stuff on the interrupt stack, and then you copy it back onto the kernel stack. So there's a lot of, a packet of information get moved around from inside the hell back into the kernel. Okay, so that information basically is the one that is going to occupy this here, so that later on you can return, back into the user state. Okay, so eventually when this guy return, you need to return back into, whatever the user thread was doing. Okay, so there's something complicated going on. All right, so we're going to look at a picture to see how this is actually done. Okay, so over here we have a program that are running. Okay, and then somebody press Control-C. Okay, so this is the instruction pointer. Okay, so you're going to trap into the, into the kernel, while all this information of the current state, they're going to be saved inside the hardware abstraction layer and get passed to the kernel. Okay, so right at this point, right, the stack pointer is going to be pointing right here. Okay, the ESP is pointing right here, and this is the frame of this particular function. Okay, so this is the user stack. Okay, and then Control-C happened. So we're going to get to this state. Okay, we're going to have the kernel stack, and inside over here, all the user register are copied from, the interrupt stack onto the kernel. Okay, so the kernel has a way to return back into the, user space. And how does kernel return back into the user space? Right, it executes a return from interrupt instruction. Okay, so if eventually we can, if the stack pointer is pointing right here, and if we execute IRET, okay, then magically we're going to pop back to the user space and return back here. Okay, so now we are going to service, now we know that we trap into the kernel, but we want to invoke this upcall. All right, when the upcall return, basically when the upcall return, we sort of want to invoke something very similar to interrupt return, so we can return back into the user space to continue execute from this point on. All right, so we need to muck around with this kernel stack to perform the magic. Okay, so this is what we need to do. Okay, so what we need to do is that we need to, copy the stuff. Right, again, the kernel is all powerful. It knows where the user stack is. It can actually manipulate the user stack. What it will do is it will copy all this information onto the user stack frame, and this frame is the funny frame that I talked about. Okay, and this funny frame is a name. It's called the sig frame. Okay, so over here we have a sig frame, and we have some kind of a, instruction pointer over here. This instruction pointer will tell it to actually execute a particular instruction. Okay, and this one is going to be called a sig return. So basically it's sort of the equivalent of iReturn, and that will allow you to return back into the user space. Okay, so this instruction understands what this signal frame looks like because it has all the user register information. So when you execute this particular instruction, it will return you back into the user space. Okay, so at this point you're in the user space, but there's sort of a shortcut for you to go back into the user space. Okay, and then what you do is that you set up, and then what you need to do is that you need to call the interrupt handler, right? Okay, where does that go? Okay, so on top of the sig frame, you set up the sig handler, right? Sig handler is a user program, right? So this signal handler is inside the user address space, okay? And now you change your instruction pointer to execute, the signal handler, okay? So at this point, you need to return back into the user space, right? So you return, so inside the kernel, you have to execute iReturn, but you have set up your stack, okay, and your context, so that when it returns, the user is going to start executing this particular function in the text segment, and the stack pointer is going to point right here. Okay, so now this guy, what happened is that when it's going to execute the interrupt handler, okay, in the user space. Okay, so now no more kernel. The user is going to execute this thing. When it returns, where is it going to return to? Okay, so it can't really return directly into the previous function. Okay, because a normal return, you saw the code for the normal return, right? The normal return, set the EBP and ESP to the same thing, pops the EBP or something like that. It doesn't restore all the other registers. Okay, so the only way that you're supposed to return is you actually have to return from the sig frame. Okay, so in this case, what happened is that when you set up this SIG handler, when you return, you want to return back to this, the instruction pointer will actually point to the stack. Okay, so when you create this SIG handler frame, you're gonna, the kernel will, actually have to muck it around so that the return address that get pushed to the stack is not the return address of this guy, but the return address of somewhere inside the stack. Okay, so this stack frame actually have code there will execute the return from interrupt. Okay, so therefore when the interrupt service routine is over, okay, we will return into this code over here. Instruction pointer will actually point to the SIG return instruction. And now this particular stack frame, the funny stack frame, when you execute SIG return, it will return back into the user space, like a shortcut into the kernel and quickly back into user space. And now you will return back to exactly where you were before. Okay? So this way, when you return, you're going to look as if you didn't really miss anything. Right? So this is the picture that we start with. Instruction pointer is pointing right here. The user stack has a function that looks like this. Okay? So when you execute SIG return, then all the registers is going to be restored into the CPU. So the CPU is as if it were in this particular instance of time. Instruction pointer point here. All the CPU register at the right value, and it's executing the function. All right, but the only difference is that this code has been executed. Okay, and this code, when it executes, it has to be in the user context, right? Because this code will change, global variable and stuff like that. So you better make sure that, when this code execute, okay, 2 slides before, it's executing using the user thread. All right, so they have access to everything there. Okay, so this is how you would, implement a signal handler. All right, so that's the last thing we want to talk about in chapter 5 for now. Okay, I guess chapter 5 has one more thing, is the scheduler. We're going to come back after chapter 7 when we finish virtual memory, and we're going to talk about that. Okay, so now we are actually going to talk about stuff that's related to kernel 2, about the file system. Chapter 1 we haven't really finished, so we're going to finish the introduction to the file system, and then we're going to go into chapter 6. All right. So chapter 1. Okay, so chapter 1, the first 13 slides of this set of slides overlap with chapter 1's a simple OS. So I'm going to sort of fast forward and sort of remind you. It says, well, the file system has these, 4 system call: open, read, write, and close. Right, very simple interface. And we talk about file descriptors, and we talk about the last thing that we talk about is this picture. Okay, this particular picture, right? In the user space, we use the file descriptor, which is the integer. Okay, and that's that's one way we get access to the extended address space, which is inside of the file system. Okay, so this one is the index into the file descriptor table, and the file descriptor table is per process. Every process has one, and that's a kernel data structure. And inside over here, there are pointer to the system file table, and the system file table is shared by all the processes. Okay, every file that's open has an entry in here. Okay, and the field inside of this system file table are reference count. Okay, so you can have one open file that actually pointed to, right? So this one count the number of pointers that point to this thing. Okay, so for another user process, they might also point to this guy. Then the reference count has to go to 2. If there's another one, go to 3, etc. Okay, this one is the access mode. When you open this file, did you open it for read only? Do you open it for read write, etc.? That gets stored right in here. The third field is the cursor position. Right, if you have read and write the file, where is the current location? So next time when you read or write, it will start from that location. Okay, and the kernel is keeping track of the file location or the cursor position. Okay, and finally, there's the INO pointer. And in one of the lecture, we'll talk about the simple OS. I guess we sort of talk about that this one, this is where we have polymorphism. Okay, we have a pointer. So this is sort of dividing line between the virtual file system and the actual file system, right? The actual file system for a particular inode, they have a different implementation. Inode represent a file, okay? From the higher level view of the file system, the VFS view, okay, you have this pointer, and all you have to do is manipulate it. With this pointer, you can invoke, read and write, and rename, make a copy of the file, or whatever you want to do. Okay, but all those things will eventually invoke it will make an indirect call to a function pointer that points to the actual file system implementation of that particular function. Okay, so over here you will call read, but read is really not a real implementation. When you call the actual read, the actual file system has a read function, and that's the one that performs the read. Okay, so that file system, that reading of the file system, is that the same as reading from the disk? Not really, right? Because the disk read is in the device controller, so that read is the file system read. So that read understands the structure of the file system. Okay, so ext2, the structure of the file system is different from, FAT32, is different from NT file system, things like that. Okay, so that file system object, the one that actually understands the file system, that's the one that eventually needs to invoke the device driver. Okay, so again, the file system has many, many layers. VFS, the actual file system, and then the device drivers, and, etc. Okay, and we're going to see that there's actually more layers. Okay, all right, so we're going to look at more detail later on, but now we are right here. Okay, so we understand that, that there are these, so I guess these objects are right here. Some people will call this the file object. Okay, so the file object has things like reference count, access mode, cursor position, and then it points to the file system implementation for this particular file. Okay, so up to this point, we sort of have a higher concept of what a file is. Right, a file has a path name to tell us what file is, and then it has some kind of a protection so that it allows you whether to read it, to write it, right? You can set a protection to have a particular file that's read-only, so therefore when you try to open it for read-write access, access will be denied. Okay, so all these things are done at the high level, okay, at the VFS level. All right? Okay, and, for your kernel 2, the name of the kernel 2 is VFS, so you'll be dealing with the file system at this high level. Okay, so at this level, if you want to remove a file, what do? Well, you can't really remove a file. You basically have to call the lower level, so this is VFS. Underneath over here, there's the actual file system. Okay, you find the pointer for remove a file from this actual file system, and you just call it. Okay, so in this level, if you want to remove a file, you don't know how to remove it. All you need to do is to use polymorphism, find the pointer, and call that particular function pointer, and then have the lower level remove the file for you. All right. Okay. So for the rest of the lecture, again, we're gonna focus our attention on VFS. Okay. When we switch to chapter 6, main focus is talking about the actual file system. All right. Okay. Let's sort of review this. Okay. So we have a small piece of code over here. We open and we read and we close. Okay. And we're gonna have a thread that's running over here. And we're going to see how the system call works. Okay, so over here, we call open. Okay, so open is actually over here we call fopen. Fopen is a wrapper around open. Open is a system call. It's going to cause a trap. You're going to go into the operating system, and the operating system is going to look at, which trap it is. It's the open trap. So it's going to invoke the function in the file system that handles open. Okay, it's going to invoke the one that's at this point is the one at the VFS level to handle the open. Okay, and in kernel 2, you get to implement open, okay, at the VFS level. All right, so what happens over here, right? Here's the trap, okay? So over here, inside the file system, you're gonna, check access rights, okay? It's gonna look at this file and to see if this, thread in the user space, right, over here, the user actually call open this file. It will verify that the user can actually have access to this file, okay? It is possible the user can see foo.txt, but there's no access, right? On Nunkey, if you try to look at /etc/password, you will get access denied, okay? Because you're not supposed to look at that file, okay? /users/etc/shadow. I guess that's the file you don't have any access. You can actually look at /etc/password, but the actual password information is actually not in there. It's in a file called shadow. All right. Anyways. So operating system over here, check access right. If access is denied, then you will return with the failure code. Okay? If it's successful, then it will continue. Okay? In this case, what it will do is that it will, allocate an entry, okay, and allocate an entry inside the system file table, right? Because over here, we use this arrow to represent many, many layers of indirection. Okay, so remember this pointer, right? This is the file descriptor table. It's per process. This data structure is inside the kernel. The kernel is keeping track of this file descriptor table on behalf of the user process. Okay, so over here, it's going to allocate an entry in the system file table. Okay, allocate this entry that it just opened, have this guy point to it. Okay, and this guy will point to something, it will point to something, and eventually it will point to the disk. Okay, so this simple arrow is just a sort of shorthand notation for all the arrows over here. Okay, so now you have a file open, right? So you're going to return back to the user space. And what's going to return is a file descriptor. The file descriptor is an index into the kernel file descriptor table. Okay, from this point on, if the user wants to do anything to this file, it needs to pass the file descriptor back to say, I want to work on file descriptor number 7. Okay, so now the user continues to execute. Okay. This says read FD, right? You're going to trap into the operating system, and again, the operating system is going to say, oh, this one is actually a read system call, okay? And then it will invoke the correct, VFS version of the read function, okay? So it's going over here, and the first thing that it will do is going to verify access right, whether you have access to read or not. It will go to, again, this one points to the system file table, okay? Inside over here, there's access, right? Okay, try to make sure that you can actually read this file. But of course, once you open it, you can read it, so that's not a problem. But if this were a write system call, if you open for only reading, and now you try to write to it, you're going to get access denied again. Okay, so over here, it will verify access, okay? And then if it's read, okay, what it will do is that it will, again, follow the pointer, okay, and eventually invoke the disk read. You're going to block inside the kernel, so this thread goes to sleep. Okay, eventually the disk interrupt is going to happen. Okay, when the disk interrupt has happened, right, then what it's going to do is that it's going to wake up this thread. Okay, wake up this thread, and then you're also going to copy the data from wherever the disk transfer, to the kernel is going to transfer back into the buffer. And it's also going to return the number of bytes that has read. Okay, so over here, we should, of course, check the return code of read to see how many bytes was actually read. So in this example, it doesn't really care. It just closed the file. Okay, so this many bytes is going to be written into the buffer when this system call return. Okay, and this is done, many, many milliseconds later because you're going to you're going to sleep in the kernel for a while for the data to be transferred into this buffer. Okay, and then finally, you close the file. Okay, when you close the file, so what does close does? Okay, what close does is that, again, it goes to the system file table and look at the reference count over here and decrement the reference count. If the reference count after you decrement is equal to 0, then this entry is deleted. Okay, so again, in your kernel 2 assignment, when you implement close, that's what you have to do. Decrement the reference count. If it's equal to 0, you have to deallocate this entry. Okay, if the reference count is not equal to 0, well, that means that there's another guy pointing to it. Okay, so when you close this guy, this entry will become invalid. All right, and then he's going to return back into user space. Okay. All right, so so let's talk about the system file table in a little more detail. Okay, to see what happened when this kind of code gets invoked. Over here, you fork a child process. Okay, and then what happened is that you close file descriptor number 1, right? File descriptor 0 is standard in, 1 is standard out, and 2 is standard error. So you close 1, you close 2, right? And then when you open a file, now this file is going to be allocated file descriptor 0. Right? Remember, this is how you pass, how you do I/O redirection. Okay, so you can say that, well, from now on, the output will go into a different file. Okay, so if I open this file for writing, that means that if this particular program, the one I'm going to exec out, if that program write to standard out, now it will go to this file. Okay, and what will happen if I do an open again? Okay, if I open it again, this file will be allocated file descriptor number 2. So if this program try to write to standard error, it will also go into this file. Okay, is that a problem? Well, if this is what you want, then it's not a problem, right? Okay, but if this is not what you want, it might be a problem. So, we sort of allow these kind of stuff to happen. Okay, so in the picture, what happened is that the second time when you open a file, you get a separate, the entry inside the file, inside the system file, inside the system file table. Okay, every time when you call open, you get another entry in the system file table. Okay, that's the rule. Okay, so when you call it the first time, this one gets file descriptor 1, right? So file descriptor 1 is going to point to this object in the system file table. And the second time you call it, you're going to allocate another entry. Remember, the rule for allocation is that you find the first available entry, and that's when you allocate to it. Okay? So file descriptor 2 is going to point to this entry, right? And then what's the reference count over there? Both of them are 1, right? Because now they're not sharing the same file descriptor, even though they're the same file. Okay, so it's kind of weird, right? Because over here, that means that these inode pointer, they all point to the same file. Okay? But, in the system file table, you have 2 separate entries. Okay? This guy's reference 1, this guy's reference 1. This guy says, when you open it for write only. This one says you open it for write only. The cursor position says both of them are 0. Right? When you first open a file, the cursor is set at 0. Okay? So what happened right now, if you write 100 bytes into standard out, okay? So then, this one, they all point to the same file. So you're going to modify that file for the first 100 bytes. Okay, what happens if you try to write to standard error? Okay, when you try to write to standard error, you are working on file descriptor 2. So, you're going to follow this pointer. This pointer's cursor position is where? It's at location 0, so it's going to wipe out the first 100 bytes. Okay, if this is what you want, that's fine. If this is not what you want, then you shouldn't be doing this. Okay, so what we really want is that we want this guy to point to the same one. Okay, so most of the time, right, if you don't want things to override each other, you want standard error to be the same place as standard out, then you will do something different. All right, so one way to do that, right, is with the following code, right? So I open, a file descriptor 1 for this file, right? So anything you write to standard output will go into this file. And now I'm going to use a separate system call called dupe. Okay, dupe says I want to make a duplicate of this file descriptor entry, right? So this file descriptor, this is 0, this is 1. Okay, wherever this guy point to, I'm going to find the next available entry in the file descriptor table and have that guy point to the same place. Okay, I'm going to have a duplicate entry for that system file table. Okay, so over here, this is, as an application programmer, you need to decide, do I want to open the same file or I want to just make a duplicate of the file descriptor? Okay, because the picture you're going to get is going to be very different. When you call dupe, you're going to end up with this picture. Okay, I make a duplicate copy of the file descriptor table. Basically, in this case, I'm just copy this pointer to this point. All right, I'm just copy whatever that's in here into this memory location, and I'm going to bump the reference count. All right, so dupe, again, in warm-up 2, you're going to implement the dupe system call in VFS. Right, that's all you have to do. Copy this one over here, increment the reference count. I'm done. Okay, so this way, when you write to standard output, what's going to happen? Right, you write to standard output, you write 100 bytes. This guy is going to change to 100. And then if you write to standard error, you're going to start writing from location 100. Okay, so therefore, it's going to look as if you're appending to that file when you write to standard error. Okay, so if this is what you want, then, this is what you would do. Okay? All right. Okay, so what about when you do fork? Okay, when you do fork, right, the child process, okay, they share the extended address space, right? So what it means is that, it gets a copy of the parent's file descriptor table. Okay, so all that happens is that, when you do fork, okay, you allocate a brand new file descriptor table. Of course, that's in the kernel. Okay, and then, the address space is exactly the same. You get a copy of the address space in the child, right? So the implementation of the fork, all you do is that you take this entry, entire file descriptor table, you just do a copy, mem copy, into this array. Okay, so, and also you have to go through every one of these file pointer, wherever that's pointing to, you want to increment the reference count by 1. Okay, so that's all you have to do as far as the file descriptor table is concerned when you do fork. I mean, as it turns out, fork is very complicated. When you do a fork, the hardest thing that you have to prepare is the address space. Okay, you want to, so when you copy, the entire address space from the parent to the child, copying the address space is a lot of work, but copying the extended address space, it's a no-brainer. Okay, you copy the file descriptor table and you're done, right? And you increment the reference count. Okay, so now both the parent and the child, if the parent writes 100 bytes over here, the cursor will change to 100. If the child writes to it, it will continue from location 100. Okay, so if this is what you want, then this is what you will do. If this is not what you want, right? So what happens is that when you fork off the child needs to close the file descriptor. Okay, and then if you want them to point to somewhere else, you have to reopen it. Okay, so be very, very careful when you write your application code. You have to understand how the kernel works so that you can have sharing or not sharing, depends on your need. All right, so we have seen in the grading guidelines the pipe character, right? We're going to say, cat, something, pipe to warm up 1 or warm up 2. Okay? Okay, so this one, we're actually using a Unix pipe. Okay, so this one allows us to take the standard output of this file and then make it into the standard input of this file. Okay, so how do we do that? Okay, so the pipe is a kernel object. Okay, so you actually need to make a system call to create this object in the kernel. And then you have to sort of connect them correctly with the file descriptor table. Once you do that correctly, then, magic can happen. Okay, we're going to see how this is actually done. Okay, so pipe is a system call that creates a pipe object in the kernel. And the pipe object normally is drawn like this. It has two ends. One end is for writing, and the other one is for reading. Right? So this end is for writing to, and the other one is for reading. So this way, you're going to have two processes that can communicate with each other, and they're going to communicate with each other using file descriptors. Okay, so this guy can call write using the write system call. Okay, if you give a file descriptor, it will write into this pipe, and this guy can read data from the pipe. Right, so this is what will happen, in warm-up number 1, right? You cat something, okay, and have this output going to this pipe. Okay, it sort of temporarily gets stored in the pipe, and then over here you read data from the pipe. Okay, as it turns out, the pipe over here, it doesn't really have that much memory. Okay, so what happens is that you can actually use the producer and consumer or the bounded buffer to make sure that when this guy tries to write too much, this guy will get blocked, waiting for this guy to read some data out. Okay, so therefore this guy can use the finite buffer to write it. Okay? All right, so this pipe is a kernel object, and it has some finite amount of buffer, and it performs this magic so that the standard out of a program can be connected to the standard in. Okay, so how is this done? Right? So when you make a pipe system call, okay, you need to give it an array of integers, okay, because you're going to end up creating a pipe object, and one end is going to connect to the a file descriptor, and the other end is going to connect to a different file descriptor. Okay, and which file descriptor that it connects to, it will return to you in this array. Okay, so when you call pipe, you're going to pass this array to the pipe system call. P0, when it returns, is going to refer to the read end, and P1 is going to refer to the write end. Again, the way I remember, which one is read and which one is write is that, remember the file descriptor 0, 1, 2. 0 is standard in, and 1 is standard out, right? So 0 is the one that you read from, and 1 is the end that you write to. Okay, so same thing over here. 0 is where you read from, right? So if you look at that pipe, okay, this will be 0 because this is where you read from, and this will be 1 because this is where you write to. Okay? And then what you can do is that, if you look at this piece of code, right, inside the child, okay, so what happens is that we have the parent process, we have the child process. Okay, we're going to create a pipe right here. Okay? So the child wants to read from 0, and the parent wants to write to 1. Okay, so our code is that the child doesn't need to have access to file descriptor number 1. So the child will so if 4 equal to 0, this is the child code. Child will actually close the file descriptor number 1, because what happens is that during the fork, the entire file descriptor table get copied. Right, so now both the parent and the child, they all point to the same pipe object. Okay, so now the child said, I don't want to write to this pipe, so I'm going to close it. Okay, and then what it will do, it will sit in a loop over here, try to read from the pipe. Okay, read is a blocking call, so if the parent hasn't written anything to this pipe, the read is going to block. Okay, so in this case, the child over here can receive multiple commands from the, from the parent, so it has to parse the input as if they're characters from, or binary data coming from this pipe to see what it has to do. Okay, and then eventually when the child is done, it's going to call x is 0. Okay. What about the parent? The parent fork is going to be not equal to 0, right? So you execute this code. Parent will close this other end because it's not going to read from it. Okay? And then what the parent will do is that it will prepare data for the child and it will write data into this pipe. Okay, so that the child can receive it. All right? So this sets up one pipe for the parent to talk to the child. If the child wants to talk back to the parent, that can also be done, but you need another pipe. Okay, so what happens is that if you have a child that needs to talk back to the parent, you need to have another pipe, and this guy will write to it, and this guy will read from it. Okay, so we only see one of them, but with this code, you should be able to set up the other end. All right, so this is the picture. All right, when you call, you're going to create this pipe object inside the kernel. Okay, and this is the read end. It's going to be connected to P0, and this is the write end. Okay, so what happened is that in order for us to, to use that in a fork, okay, when we create the child process, we're going to get an exact copy of this file descriptor table to right here. So therefore, that means that, this end will be the read end, and this end will be the write end. Okay, so then you need to close the right places, right? The parent will close the read end, and the child will close the write end. So two of those pointers disappear. Okay, so now you can see that if the parent write to this guy, it will go into the pipe. Okay, so the pipe is kind of like a device, like a disk. Okay, except it's faked, right? Because when you write to the pipe, you're making a system call, so the operating system can do all the magic for you. Okay, so it will write to this pipe. Okay, and then you can read from this pipe in the child. All right, so this is one pipe. If you need, two pipes, you can or three pipes for some reason, you can set it up any way you want. All right, so the command, your login shell, right? They can, set things up so that this procedure works by using the pipe. Okay, but this case is a little different, right? So if you are doing the login shell, okay, and if the user type in a command like this, what do you have to do? Okay, it's different from the previous picture. Okay, because what happened over here is that you need to create one child process, and then you're going to create a second child process, and then you have to connect the file descriptor table between these two childs. Okay, so remember that this child process, when it runs, it only knows about standard in and standard out, right? It doesn't know about anything else. Okay, so therefore, it's the job of the login shell to mess around with standard in and standard out and standard error. Okay, so it's going to create these two child, and it's going to create a pipe object, and then connect the file descriptor table so that they connect to the right way, and then only at that point it will set things up first, and then it will fork the child processes. Okay, so that when this child processes get forked, its standard out is going to connect to the pipe, so that when this child process when it starts to run. Let me make a correction. I guess I should distinguish between forking the child process and making the exact call. Okay? So when you create the child process, you got to keep in mind that the file descriptor table will look like this. So you will create two child processes, and before you do the execl call, right? This one is going to get one execl. This one is going to get a different execl. Before you do the execl, you connect the pipes to the right place. All right, so you can use this as an exercise to try to see, well, if you are the login shell, what kind of code you have to write to make this thing work. All right? Okay, so the read and write system call performs sequential access. Sometimes you don't want sequential access. You want to, if you have a really large file, you just want to jump into one location, inside that file. Okay, so what do you have to do when you want to do that? Okay, as it turns out, all you have to do, right? So think about this, right? You have a file descriptor table. This one points to the entry in the system file table, right? Okay, if you want to jump to a particular location in 5 minutes. All right, thank you. Okay, what do you have to do? all you have to do is to set location to be equal to whatever you want to jump to. Okay, if you set this location to be 1 million, right? So you have a 1 gigabyte file. If you set this one to 1 million, next time when you read, where would you read? You will read from the cursor, right? Okay, so this function is called lseek. Okay, it's a system call, and again, you have to implement that in kernel 2. So what it does is that it takes a file descriptor, tell you which file to manipulate, okay, and it tells you, where do you want to change it to, okay. So there are 3 last parameter tell you. Last one is kind of the how parameter. It tells you or relative to where do you want to seek to, okay. When you say seek n, that means that you want to seek relative to the end of the file. Okay? So the operating system knows how big this file is, so you know where the end is. Okay? So this one says seek to the end minus 1. Okay, so if you think about this file, it's just a stream of bytes. Right? Here's byte 0, 1, 2. Right over here, this is the size minus 1. Okay, so this particular call says seek to the, so seek to the last position, which means that the location is going to point to this, the last location inside this file. Okay? There's another way you can do it. You can call seek current. That's wherever the current position is pointing to. Okay? And then you can add to it or subtract from it. Okay? So this one says seek current minus 2 so that the file cursor position will be decremented by 2. Okay? So what is this code doing now over here, right? You go seek to the last byte, okay? While this pointer is not equal to 1, what you do is that you read 1 byte and you write 1 byte. Okay? So you go to the last place, right? You read 1 byte. When you read 1 byte, you increment the file cursor to be right here, to be the end. Okay? And then you write this byte out, right? So you read this byte in and you write it to standard output. And then you do lseek, seek current minus 2. So you use the current position, you subtract 2. You're at the second to the last byte of the file. Okay? And then you read 1 byte, write it out, and then go back to the 3rd byte. So basically, this program reverses the bytes in a file and print them out. All right? So this is a complete reversal code over here. Okay? So there's one that we haven't seen. This is called the seek set. Seek set says go to the beginning of the file. So the the offset that you're specifying over here is relative to the beginning of the file. Okay, so if you say, seek set, you say 1 million, as your offset, then you will go to the 1 millionth position inside the file. Okay, and I mentioned before that, in Unix, when you want to, make the file bigger, all you have to do is to write beyond the end of the file. Okay, so actually, if I have a file that currently is of size 0, if I call a seek to location 1 million, is that allowed? Actually, you're allowed to go there, right? And all you have to do is if you write 1 byte in there, now your file is 1,000,001 byte long. Okay, so it's really easy to create a big file. All right? Okay, I guess this is the good point to break. Next time I will finish chapter 1, and then we're going to go into chapter 6 to see how the actual file system gets implemented. All right?
This has been CS 402 on Wednesday, June 25th, 2014.